When we have a wire between or within a magnetic field, and we move that wire across the magnetic field, we get an induced EMF, an induced voltage, and a current through that wire. So if we connect this wire up to a voltmeter, as we move this wire down between the poles of the magnetic field across the magnetic field, we get an induced voltage, we get a current flowing. If there's a complete circuit, we get the voltage. To find the direction of that current, we need to use our right hand slap rule again. When we think about it, let's consider this wire that's being dragged down. This wire, we could consider it being full of positive charged particles. And in pulling the wire down, we're dragging these positive charges down. That's equivalent to a current downwards. And then when we consider the magnetic field, direction of the magnetic field from north to south, then using our right hand slap rule, the positive particles in the wire is going down is equivalent to a current going down. The magnetic field from north to south, right hand slap rule, these positive charged particles will be moving in this direction, so we get a current I in this direction. We can draw it this way. Imagine we've got a magnetic field B into the page, and we've got a wire across this page, and inside this wire we've got positive particles and we've got negative particles. Let's consider what happens to these positive particles if we move the wire in this direction with a certain speed. Let's consider, as we're pulling this positive particles down, that's equivalent, all these positive particles going down, it's equivalent to a conventional current moving in this direction. So we can say we have a conventional current in this direction. The magnetic field is into the page, so these positive particles will experience a force to the right. So as we move this here, these positive particles will migrate to the right hand side. Let's stop and think for a moment what happens to their negative particles. As we are pulling these negative particles down, it's equivalent to a conventional current this way. So what is the direction of force on these negative particles? As they're going this way, it's equivalent to a conventional current this way. The magnetic field into the page, the negatives, that particles then will experience a force to the left. So just as the positive particles are experiencing a force to the right, the negative particles are experiencing a force to the left. That will leave us with this situation here. If we extend our magnetic field here, that will give us a situation where the positive particles have migrated to the right end and the negative particles will have migrated to the left end. This will then leave us with an electric field and a voltage. If we were to connect our voltmeter across the ends, we would get a voltage. And if we completed this as an electric circuit, we would end up with a current flowing. This is the source of the induced EMF in a current carrying conductor moving through a magnetic field. We've got here a situation, 4 situations, where we've got a wire here being moved in a magnetic field to the left. So we've got a magnetic field sticking into the page. We've got this wire travelling to the left with a velocity v. What happens to the positive and negative particles in the wire? Let's think for a moment. If we think positive particles moving in this direction is a conventional current this way, the magnetic field is into the page, the positive particles then will be moved this way, and the negative particles, a negative particle moving this direction is equivalent to a conventional current going this direction. So we've got on the negative particles a current this way, a magnetic field into the board. The negative particles are going to be moved to the top, and again we'll have an electric field set up, positively charged and negatively charged. The second example, the wire is moving in this direction, it's moving up. What happens to the positive charged particles in this wire? Positively charged. As we move a positive charge in this way, it's equivalent to a current in that direction. The magnetic field is into the page, so the positively charged particles will experience a force to the left. The positive particles will move to the left, and if we do the same with the negatively charged particles, we end up with the negatively charged particles over there, and we end up with a voltage difference, a potential difference, what we call the induced EMF, or voltage. So calculating induced voltage, remember we've got a magnetic field between the poles. As we bring this wire length L within the magnetic field, length L, as we move it with a velocity v, the voltage, the induced voltage between the ends, the induced voltage is equal to B VL. The induced EMF, the induced voltage, is equal to the magnetic field strength in Tesla, induced EMF of course in volts, times the velocity. We've got to keep our wits about us. The capital V is voltage, the small v is velocity in meters per second, and L is the distance, the length of the wire in meters. V is equal to BvL. So for example, if we have a length of wire 0.8 meters, 8 meters length, and it moves through a magnet of magnetic field strength 0.01 Tesla at speed equals 25 meters per second. What is the size of the induced voltage, the induced EMF? The voltage is equal to BvL is equal to magnetic field strength 0.01 times the 25 times length, remember 0.8 meters, 80 centimeters, 0.8 meters, 0.8. The voltage is equal to 0.2 volt. Another question, calculate how quickly a 0.4 meter length of wire must be moved through a 0.2 Tesla magnetic field to induce a voltage of 3.2 volt. From our equation, induced voltage is equal to magnetic field times velocity times length, and we want the velocity, how quickly the velocity. So let's rearrange the equation. Velocity is equal to V divided by BL equals 3.2 divided by 0.2 by 0.4 is equal to 40 meters per second. Pretty powerful that, isn't it?